Okay, we're back. So let's take a look at another way to do the associate command. We are going to start a new markdown file again, and we can store this just for our own practice. We can call this association 3, and this is just practice. Call it whatever you want. It's fine. We can make it as an HTML or Word, whatever you choose. But this will allow us to make our own markdown file as we've been doing for these. And we can store them and come back to them later just for practice. And as I keep saying, you can send them to your friends and be like, here's the one I made for practice. And even type in your own interpretations. This is an excellent way. I feel like there should be a file sharing. You guys are like, yes, yes, yes. I feel sometimes I make things and people don't use them, but if everyone made their own and gave their own interpretation, you could read over everyone's interpretation and see if you agree. Maybe we'll try to do some more of this in the future. But for now, let's focus on this one. Well, we need to load library reg class. Good old starter out commands, load library reg class. Once again, using Control Enter to run the commands. Now we're going to load in the data here. Let's go survey. I like survey 10 because it doesn't have the numbers before it. I've always liked survey 10. And let's read the names in survey 10 again. So that's just loaded in the data. And now we're looking at the names. I like it because I just like seeing gender, weight, height. Survey 11 has them a little bit differently, and I don't like them as much. These were Stat 201 surveys done, and so let's load that one in. Take a look at the names inside of survey 11. And you'll see it has the X variables. It just makes it a little bit more confusing looking in the output, so I often don't use those for that reason, because I like survey 10 just has it this way. Of course, in other data frames, it's harder to look at and see which variable you're looking at. And that's one of the great things about R. This is nice and quick and easy. So I'm actually going to use a command you might have seen me use last time to remove a data frame. I'm going to remove survey 11 since I'm not using it, and that took it away right there. So just took it out of my environment. Okay, so we've got everything loaded in now. Let's just call this analysis again. Analysis, and I'm pretty sure this has, nope, doesn't have typos or typo check. So sorry if I have any sort of typos in here. I try my best, but I can't spell. So this time, what are we doing this time? We are doing the associate command in the reg class package, so make sure to have that on, and we are doing it for 2 quantitative variables. So let's go ahead and run the associate command for 2 quantitative variables, and this will be y tilde x. So we need a quantitative, and we're going to go easy here first, kind of classic. We're going to see if somebody's height can explain their weight. Once again, we are using a data frame, and the data frame has our variables inside of it. I've explained many times that since the variables are inside the data frame, you have to call the data frame. As you can see here, I was looking at what's inside the data frame. I have height, I have weight, and those are all inside of survey 10, so I have to tell it survey 10 over here. If they were just floating out in the ether, just out in the open, as just being values, we wouldn't have to call data. So let's go ahead and run the associate command. Here we are. So it's saying the figures, the plot margins are too big. So I'm going to go ahead and increase this all over here for a moment. And let's make it a little bit bigger. Now let's run the associate command again. Now it doesn't get angry. And we get some interesting plots here. So we have a little bit less analysis. Just going through right here. We have p-values, but let's look at the plots first. So looking at, let's zoom in. Here we are. We get a scatter plot with histogram borders. So these are the histograms for the univariate. Histograms are univariate. So we have a histogram of weight. We see a lot of people are in the 120s, 130s, 140s, and then we get a right skew to it. It's right to the high, left to the low. So be careful, because if you were to turn this over, you'd be like, well, it's left skew. No, it's right skew because it's to the high side. Remember, if you were to flip this, your high end would be 300 would be on the left if you were just to fall this over like that. So it is actually skewed to the right, right to the high, left to the low. It's a good way I remember it. Where we see heights, heights have a little bit of an interesting characteristic to them. They have a few outliers here, and these are people who probably misentered their height, thinking that we wanted them to put in they are 55, or excuse me, they're 5 feet 5 inches. And thus they put in 55, because we have a lot of people who are short for about 900 or so observations. We can look at the observations here in a moment. Actually, I think it's 699. There are 699 observations. So for the 699 observations to have 1, 2, 3, 4, 5, 6, 7, 8, 9 people below, even more people below 5 feet tall, it's just kind of a good many outliers that you would not expect. And like I said, it's probably people misentering the data, but people are that short. So what do we generally see? If you notice right here, we have going through here kind of a line. It might not be perfectly linear, and that's what we want to assess first, is the linear relationship going on between this x and this y. Is it mostly linear? Yeah, I'd say it's mostly linear. A little bit of a bend. I don't know. It kind of flattens out there, kind of goes linear, and then I don't know. Is it perfect? No. Is it all right? Yes. I'd say there's a linear relationship between height and weight, and that makes sense that people who generally are taller generally weigh more. And that's just a real simple way of saying it's a positive linear relationship. And that's what we're doing right here. We're examining the correlation between these two variables. And correlation, at least when we talk about Pearson correlation, needs to be linear. So we have Pearson and Spearman. Now, let's go down to these two plots. If there was no correlation between these two variables, we would see zero correlation. And Pearson is specifically linear correlation. That is the kind of relationship we want to see for Pearson, is that is well described by a straight line. So this one does look to be decently described by a straight line. I kind of like it. And what do we see over here? We see our results. Our results, our Pearson correlation is 0.601. And we see just as extreme as our results, because both of these would be just as unusual. Because it would be very unusual to get perfect negative correlation, very unusual to get perfect positive correlation. That's why when we talk about a p-value, we talk about the probability of our results or results more extreme. And this is just as extreme as our results, and then if we were to go to the outside, it'd be more extreme. And you can tell the simulated p-value here is 0 because the probability of results as extreme or more extreme than ours is 0 because there's no results in our simulation that were simulated beyond ours. Because you would not get this pattern of points at random. This is put together by something that seems to not be random. You could get it at random because randomness can do anything, but it's very, 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 very improbable. And so now we look over at the Spearman, which shows the same sort of thing. Our Spearman's actually a little bit stronger, so that's got me wondering, maybe I should talk about it with a Spearman because it is monotonic. That's making a good case. I see a difference between the Pearson and the Spearman, and maybe there's a little bit more well described by a monotonic, positive monotonic relationship. And let's just mention what monotonic means. Monotonic means it goes in one direction. So you see down at the bottom end, it is just going like this, then it starts to go up, and then maybe at the end it might start to level off again. It makes like an S. But the S never goes down. We don't see a dip here never goes up. We don't see a dip. And you see, that's not really, it's just a few points. But if we were to really go up like this, that'd be not described by a monotonic. Or if at the end, let's go through it, if at the end it started to go down, that wouldn't be a monotonic either. So we want to see one direction for monotonic. And I'm starting to reconsider now. You have to make a case. And for the most part, except for the outliers and the extreme sides, it's generally well described by a Pearson, but I'm starting to have my doubts now when I see that Spearman is that much stronger, because obviously Spearman is picking up on something that Pearson didn't. And usually those numbers will be close, and we use Pearson by default. As you can tell, you kind of just have to look at it and analyze the results and go step by step by step. So let's look at the p-values now. And the p-values are going to be generated, and I'm making it a little bit bigger so we can see a little bit better here. And I'll just make it nice and large right here. Okay, so let's scroll into our results, and here we are. So we do see a big difference between the Pearson and the Spearman. Once again, the Pearson is just giving us the idea of the linear relationship between x and y, and this is a moderately strong positive linear relationship. It is very unlikely to have occurred by chance given the p-value, so we know it is statistically significant. The Spearman just tells us the strength of the monotonic relationship. Generally, we use this when it is nonlinear or there's outliers. And so it's kind of making a good case that we should use it for this one here. It is also very statistically significant, so there is a pretty strong positive monotonic relationship. And what this means when we do the Spearman is everything is ranked. So if you have something that is extremely large, like 2 million, and then the next largest observation is only 100, well, that 2 million will only be one rank higher than 100. So it downweights outliers. Meanwhile, that could totally influence the Pearson R. It won't influence the Spearman. So it's a good way to handle outliers and to handle nonlinear relationships that are still monotonic. That is key, that it has to be a monotonic relationship to be Spearman. And lines are monotonic, so Pearson does handle only monotonic also. So let's look at the confidence intervals for our p-values. Both of them are extremely significant. And if you notice down here, we do have advice again on which ones to use and advice on a transformation if we want to fix everything. So it's really great because it tells you what to do. So let's maybe try something a little bit different. It's hard to find perfect relationships between all these, but let's see what we can do here. I'm going to move this in a little bit here and put it to a 2. I like it when it's just 2 per. Oh, it's all crazy again. We had such nice, pretty output before. There we go. Looks nicer. Number of tattoos, that's quantitative. Number of phone contacts, that's quantitative. Let's see here. Actually, I think I know the way this one looks. If we use this, let's do body piercings by weight. And I think I know we don't want that to do that. Let's go ahead and run this right here. And actually, this is, as you can tell, it's much better described by a Spearman. So what we see here is a bunch of people who weigh very little, and they have a lot of body piercings. Meanwhile, when we get into the higher weights, we generally see fewer body piercings. And this is also a good example of a lurking variable right here, because the lurking variable is gender, because this is really male-female differences. But we can't use that to describe it, at least for this association, because right now we're only doing scatter plots. So what we see right here is a monotonic relationship. It's a negative monotonic relationship, as it is. It goes down, but it never goes back up. It just kind of flattens out. I know we got that outlier up here, but just ignore that. And just goes like that. You'll also notice that our Spearman is more significant than our Pearson. Actually, they're both technically as significant, but our Pearson is lower in correlation value than our Spearman, and they're both negative. We can view that over here in the results, and there is our results. And this is definitely a good indication that the Spearman is picking up on something the Pearson doesn't. From our plots, we see it is more well described by a monotonic kind of bent line than it is a straight line. And also we see that there are a few outliers, all of which indicate to us a Spearman. So sometimes when you see these grand differences right here, it's really best to use the Spearman. And you don't use it because it's the highest. You use it because it's better described by a bent line. And because of that, it is the highest. So the reason is it's better described by a bent line, and this line only goes in one direction, and thus the straight line does not describe the relationship well enough. So Spearman is a great alternative to Pearson when a straight line does not describe it well. And once again, we have very extreme statistical significance right here, and all of our confidence intervals for the significance come out significant also, conclusive, I should say. Let's see if we can run one more here. Number of video games hours per week, percent dateable, percent more attractive than, percent funnier than. Let's see here. Do people who think they are funny, does that explain if they think they are more attractive? We do intelligence also. So we're using the X funnier than to explain if people think they're attractive. Because they're saying, I'm funnier than this amount of people. Well, how attractive do you think you are? And we should kind of think about what we're going to get first. I would think I'm going to get a positive correlation right here, positive linear correlation, probably maybe R equals to 0.3, maybe 0.2. I'm going to go 0.22. I haven't ran this yet, so let's see. Oh, no, it's a lot stronger than I thought. Obviously, I haven't ran this. But if you take a look at the plot right here, you will see a line going through it. And this is actually probably our best Pearson right here. And you'll notice our results right here are near 0.5. I guess it didn't make it. It's probably 0.48 or 0.49. Let's take a look. 0.49 actually made it to 0.52 for the Pearson, which now the Pearson's higher. And once again, we don't just use the Pearson because the Pearson's higher. We use it because it's better described by a straight line and there's not really any outliers. And because of that, it is the highest. It's like, well, the reasons for it is this, and it's usually better because of that. If there was ties, we'd have to make decisions. But first, look at your plot. A straight line well describes that there's not many outliers. That is a Pearson. So I'm glad we finally got one that's actually a good Pearson. And this obviously is extremely unlikely to happen by chance. You might say, oh, this looks like a blob of points. But if you actually make an ellipse around it, it's really good. So I know we're just skimming through a bunch of output right now. We went to the first one in depth. Let's get a really bad one right here. Let's do minutes per day on Facebook. Let's get something that probably won't describe something else. And let's see if people being, aha, great. This is garbage. If you notice, our results could occur due to randomness. And that's what's being shown down here, is if we were to do permutations, how often would we get a correlation as extreme as ours by removing the association and just putting them together randomly? So this is excellent because this shows a very large p-value, probably in the neighborhood of 0.6, 0.7. There it is, 0.6 and 0.5. Neither of these are statistically significant, and you can't just look at the Pearson value or the Spearman value to say if it's statistical significance. Just to make sure you know, statistical significance is only noted by the p-value. Practical significance is when I actually talk to you about this and we try to use it. And we could try to use the last one right here. Let's go back to a practical significance, because key part right here, for it to be practically significant, it must be statistically significant. For it to be practically significant, it must be statistically significant. So here we are with our, if people think they're funny, they generally think they're more attractive than people. It's pretty strong correlation. And actually, since correlation's about, 0.52, R squared would be 0.25 or so, 0.25, 0.26. It's pretty high R squared, 26% of the variation in the percent people think they're more attractive than is explained by the percent people think they're funnier than, because it's doing the explaining. Maybe if you want to boost your self-esteem, you take a comedy class, like maybe, and there's no cause and effect relationship right here. It's not a physical law, but like if we find funny people, we would generally expect them to have a higher sense of attractiveness. It doesn't mean, once again, that if you become more funny, you'll feel more attractive. But, I like to say that maybe there is something to that. When people think they're funny, it boosts their self-esteem, and maybe with a boost of self-esteem, they feel like they're more attractive. We don't know that, but further investigation would be needed. Why does this exist? I don't know. It's a lot to go on there, but how we wish to use this, there might be some way. I keep talking about, like, how could we use this at UT? And I don't know, maybe you're setting up a social or something like that. So you said, I don't know, it's a comedy social. It's a comedy club. I don't know. I have horrible ideas these days. And so does this seem practically significant? Yeah, it does, because it seems like it explains a lot of variation. And that's what I'm pulling at, is I'm pulling at the R squared right here by squaring Pearson. About 26% of the variation, because I'm squaring 0.52. 0.5 squared is 0.25, so it's about 0.26. About 26% of the variation is explained. That's a lot of variation. And I feel like this does a pretty good job of understanding people's feelings about how attractive they are by knowing how funny they are. And that does it for this. If you have questions, feel free to email me. Good luck.